let me introduce you to this concept. So, I am looking at a new concept called potential. Well, since we are still dealing with electrostatic cases, I am looking at electrostatic potentials. Okay. This electrostatic potential is sometimes denoted by phi or sometimes denoted by V. Okay. I will use V for now, but sometime later I might switch to phi. Okay. It does not matter which one you use, both terms are equally used in literature. Okay. So, if I want to define electrostatic potential, let me first talk about the point charge. Okay. So, go back to the point charge over here, we know how to calculate its electric field. So, there is an electric field out there. Okay. Now, I choose a particularly interesting electric field pattern, right. Let us say I do not want to choose the point charge, I choose a particularly interesting electric field which I somehow have generated, in which the electric field is pointing horizontally and it is all uniform along this particular direction. Okay. Such an electric field we have already discussed how to obtain. You can have a long line of charge and this is essentially the electric field that it would be producing, except that its magnitude would be decreasing, but here I am going to assume that the magnitude is same. Okay. Now, consider 2 points here, consider a point R2, consider a point R1 here. Okay. Now, imagine that I am taking a particular test charge delta q. Okay. I am taking a test charge delta q and I am going to move this test charge from R2 to R1. Okay. I am going to move the test charge along this red path from R2 to R1. Remember that my electric field is uniform, which means that its magnitude is not changing and its direction is also always along the horizontal to the right. Okay. So, I am moving from R2 to R1. Okay. Now, I know that if I do not move it, right, if I just keep the test charge at the position R2, since the electric field is directed to the right, the charge would have simply accelerated to the right, because if I have a test charge delta q, okay, there will be a force acting on this and the force will be E times delta q, correct. The force acting on the charge delta q is E times delta q, and if I have to move the charge from one point to another point, okay, what I would have to do is I have to perform some work. Which way I am performing the work? I am actually moving this charge from against the field, right, from point R2 to point R1 against the field. Field is pointing to the right, but I am trying to move to the left. So, I have to expend some energy, I have to perform some work in order to move this point. How much work should I perform? Work done must be equal to the force that I apply times the distance I move. So, this is again from the mechanical concept of moving a block. Okay. So, I have a block, I move it a distance of d and I apply a force F, then I will, the work done will be force into distance. I will add a negative sign here just to indicate that this work is done against the field. Okay. Since I am doing the work, because I have to move this charge from R2 to R1, I am doing work against the field. This is a work that is being done against the field. Okay. Work done is force into distance. What is the force? Force is E delta q, which is the test charge times the electric field at that particular point, times the distance. So, let us say I have moved a distance of R2 minus R1 over here. Okay. Along this path I have moved a distance of R2 minus R1. If I now define how much work I need to perform in order to move one unit charge, okay, I define this as the potential. Okay. That potential will be equal to minus E times delta r, where delta r is the length along which I have moved or the distance I have moved. Okay. And this potential can be represented as V. So, V is equal to minus E into delta r, or sometimes you can see that the same thing it is written as minus E into delta x, because this is a x and y plane, you can either do that one. Okay. I am going to use E into minus r minus delta r for now. Okay. So, this is the potential. Now, what significance has the potential? You remember from your mechanics courses that potential, if for example, you have an object which is lying at sea level and we take this sea level as the origin, and there is a mountain on the sea, you know, like adjacent to the sea, okay, not on the sea, of course, there will be adjacent to the sea, there will be a mountain. Suppose there is an object up here and from that height the object falls down. Let us say this mountain is about 100 or 1000 meters high from the sea level. So, when this object drops down, all of the energy that this object possessed by virtue of it being top on the mountain would actually be converted into kinetic energy as it drops down, right. However, how did this object get up there? How did the object manage to get itself up to the mountain? Someone had to take the object from the sea level up to the mountain. So, someone must have done work, and whatever that work that someone has done gets stored as a potential energy, or we say that this particular on the mountain top the potential is say 1000. It means that there must be 1000 units of potential energy that would be that one can harness to convert that into kinetic energy when you drop the object. Okay. Very similar to this one. Suppose if you take the charge and put it at the point R1, okay. So, you move the charge delta q from point R2 to R1. If you now just leave the charge, if you just stop now, the charge will move on its own because the force is pushing on this one. The charge will move and it will get accelerated. There will be a kinetic energy. However, that kinetic energy when it goes from R1 to R2 will be the kinetic energy, which will be the energy that it has expended from the potential energy that it has gained by someone moving the object. Okay. So, if someone moves against the field, we are imparting the energy to the object, and then the object can actually convert that energy, potential energy, into kinetic energy. Okay. So, this is the potential is minus E into delta R. Note that the fact that this potential is work done against the field is indicated by a minus sign. Okay. So, this is important, we will later see why it is important. Okay. Now, here is where that Newton per Coulomb and volt per meter thing comes from. Okay. You have work done per delta q. What would you think as the units of work? Work will be force. Force is work done is newtons times meter, right. Newton times meter is the work done. Okay. Work done per charge will be Newton per Coulomb into meter. Okay. But we have also seen that for the potential, right, this is electric field for the potential. So, we have seen that work done per charge is the potential. Okay. In SI units, potential is measured in terms of volts. Okay. So, work done per charge is potential, which is measured in volts, and work itself is measured in terms of joules, right. So, I have the potential, this is volts, okay, sorry, this is volts, work is joules, okay, per charge, but work done was also equal to E times delta R. Okay. E is the units for which we are looking for, delta R is the distance that I am measuring. So, this must be equal to meters. So, the units for E might turn out to be joules per Coulomb. Okay. So, charge is Coulomb per meter. Okay. However, we have also seen that potential itself is nothing but work done per charge. So, we have seen that the units of electric field will now be written as joules per Coulomb into meter, but we have also seen that potential is defined as work done per Coulomb, right. Electrostatic potential is work done per Coulomb. Work done per Coulomb is nothing but joules per Coulomb. So, I can replace this joules per Coulomb into volts, thus giving me electric field units of E measured in units of volts per meter. Okay. So, this is where the units for electric field comes from, volts per meter. If you recall, we had a uniform electric field in a given region of space. This electric field over a small distance, at least we can consider it to be constant. Let the electric field be directed along the horizontal to the right side, okay. And then I pick 2 points over here, call these points as R2 and R1 if you would like, and then I will define or I will find out what is the amount of work that is required to move a charged particle from, or a test charge from point R2 to point R1. Please note that this movement is against the electric field. We will take this against the electric field into account when we write down the expression for the work done on the charge. So, work done on the charge is the force that we are applying times the distance that we are moving. So, if I call the distance as delta r, and delta r from this figure can be easily seen to be r2 minus r1. Okay. So, when I move a distance of delta r along this particular path, okay, against the field, I will be performing some work, but I know that the force on the test charge is also given by the electric field at that particular point, and we are assuming that the electric field is constant as we move along from R2 to R1. Okay. So, what we actually get is not exactly, I mean, although this is work done, if we divide this work done from the test charge, that is to say, if we calculate what is the work per unit charge or work per test charge, that will give me the potential. Although here we have shown that this is the work done, one should actually think of this as differential amount of work done, that is, what is the extra amount of work that we need to do in order to move the charge from R2 to R1, assuming that the charge has already moved from some point to R2. So, in a sense, what we are getting from this equation is not the absolute potential, but the potential difference between R2 to R1. Okay. So, with reference to some zero potential, this quantity that we have just written down is actually the potential difference between the points R2 and R1. So, you have delta V is equal to minus E delta R, because I assume that the direction of movement is along a certain R direction. And what is the potential difference here? It is the potential difference between the points R1 and R2, which is equal to minus E delta R. Now, there is no rule or there is no requirement that I should always move along the line that is parallel to the electric field. Okay. Sometimes I might choose a path in which the electric field would be making an angle with respect to the path along which I am moving the charge. Okay. In that case, how does this definition change? Well, you know this already from mechanics, that if I take a particular object and I apply a force, the force will move the object, and the force is in line with the displacement of the object, then the force experienced by the object will also be maximum, right. However, if I now pull or push this object, if I pull this object for example in this direction, not all of the magnitude of the force is experienced by the object. How much force is actually experienced by the object, or how much work that is done by the object, is given by the dot product between the two vectors. So, if I call this delta x as a vector, or I can call this as delta x into x hat as the vector element or the direction along which I am moving, then the amount of work that is done is actually the dot product between the two vectors f and the displacement vector, right. So, I know that the amount of work done is f dot delta x, and in case we let delta x go to 0, in the limiting process delta x go to 0, this becomes dx. So, the work done or the differential amount of the work done will actually be equal to f dx, sorry, f dot, there is an x hat here, dx x hat. Okay. So, this is the amount of work that is done. Now, with the same analogy over here with respect to the electric field, we can now write down saying that the voltage difference or the differential amount of the voltage between the 2 points, if I move a distance along dx, is actually given by minus E dot dl. Okay. What is this dl? If you remember the coordinate systems that we talked about, dl was the line element, right. It is actually the vector in which gives you the direction of movement. So, if I move in an arbitrary path, then that arbitrary path movement can be characterized by a line segment, which is a vector line segment, which is dl. Okay. So, now if I pick 2 points B and A, let us say, so I am moving the charge from point B in the space to another point A in the space. Okay. So, I am picking up a particular path over here. The path, the total potential difference between the 2 points, or the potential difference between the 2 points A and B, will be obtained by integrating this expression dV is equal to minus E dot dl over this entire path. Okay. So, if the path is given a name called C, then the potential difference between the 2 paths, namely V at A minus V at B, okay, this potential difference will be integral from B to A E dot dl. What is E and what is dl? dl is the vector element, line element here, and then electric field is the electric field of the region of space in which we are moving the charge. Okay. So, this expression is very crucial for you to note. The potential difference between the 2 points, okay, is given by the line integral of the electric field, which is a vector quantity along a particular direction. So, note that both the electric field as well as the line segment both are vectors. Okay. So, you need to specify the direction of the path as well as you need to specify the corresponding values of the electric field at each point in the path that you are taking. Okay. Now, there are certain very easy consequences that we can find out. One of the things that has happened over here is that the left hand side is actually a scalar, okay, and for the electrostatic field that we are considering, this line integral or the path integral is completely independent of the path that you have chosen, and it depends only on the endpoints of the path. Okay. For example, if I take one path from point B to point A, okay, say I go straight up along this path, then the potential difference will be some delta V. Okay. This delta V is V of A minus V of B. Okay. So, this is some potential that you are going to get if you follow the path number 1, which is a straight line path from B to A. Suppose you do not go straight from B to A, let us say you go from B to some other point C, and from C you head to point A. Okay. Of course, you are still going to the same final point, but you are now taking a different path. So, let us call this as path 2. It can be shown, okay, that for the electrostatic fields that we are considering, this line integral or the potential difference will not be a function of the path that I have chosen. Okay. All paths with the same initial and final points will lead to the same potential difference. Okay. So, delta V is independent of the path. So, this is one very important observation. Let us mark it down. Delta V is independent of the path. And it depends only on the endpoints. Okay. You could choose any path and this will depend only on the endpoint. Now, a plausible explanation for this particular observation that we have made can be obtained by looking at the point charge fields. Okay. So, these are the point charge fields that I have. Now, imagine that I am looking at moving from along this particular path from this point, let us call this as R2 and this point as R1. I take this direct path. Okay. Here the electric field is along the direction of along the radial direction, which means that along this path 1 the electric field is opposite to the direction of the line segment, but essentially they are parallel to each other, right. So, parallel, but in the opposite directions. So, there is some amount of potential rise or potential difference that would happen as you move from R2 to R1. Okay. So, if you take path 1, you are moving in parallel to the electric field, because electric field is also directed in the same line, but it is in the opposite direction except. So, when you move from R2 to R1 against the field, there will be some amount of potential difference. Now, this is the xy plane, okay, because I am looking at a particular plane, these are the field lines in this particular plane. Okay. We will talk about other different coordinate system in which the electric fields are properly given for a point charge later. Okay. Now, suppose I take a different path, let us say I go from R2 to R3 perpendicular to this line, okay, and then I go straight up from R3 to R1. Okay. So, I go from R3 perpendicular to R3, actually let us not do it this way, let us go again from R3 to R4 and then go back from R4 to R1. Okay. So, this long winded path that I have taken from R2 to R3, R3 to R4 and R4 to R1, and please note that the direction is also very important, right. So, I cannot say R2 to R3 and then R4 to R3, it does not make sense. So, these paths whatever that we are drawing are directional paths, that is there is a direction associated with the curve. Okay. So, we will come back to the direction sometime later. Now, you have R2 to R3 movement. Now, what is the direction of the electric field? Assume that you are moving in this way, what will be the electric field? That would be sorry, for 1 second, let us let us not consider the point charge. Okay, let us consider the uniform electric field that we are considering. Okay, sorry about this one. For point charge, the path that I have chosen is not exactly correct. So, we will come back to that point charge in a little bit of time. Okay, let us go back to the uniform electric field itself. So, I have the uniform electric field going along horizontal to the right as we have considered so far. Now, on this electric field, I am moving from R2 to R1 by taking a path from R2, R3, R3 to R4 and R4 to R1. Okay. So, I move from R2 to R3 and R3 to R4 and R4 to R1. While I move from R2 to R3, the electric field is always perpendicular to the direction of my movement, right. So, I am moving vertically downwards from R2 to R3, but the electric field is directed to the horizontal and to the right. So, if you again remember the force and the object analogy, if I apply a force perpendicular to the object does not move, no work is being done, energy is expended, but no work is being done, okay, because the object is not moving. So, with the same analogy over here, I can move the point charge perpendicular to the electric field and I will be doing no work. Okay. Now, once I moved from R2 to R3 without any work, I am now going to move from R3 to R4. When I move from R3 to R4, I will be performing some work against the field, and this amount of the work will be exactly equal to the work that we have obtained if we are taken from R2 to R1, okay, because this is parallel to the direction, it has the same length here, and the electric field is the same value from this path R3 to R4 and R2 to R1. So, because of this, the work done or the potential difference that I have accumulated or the potential rise that we have seen will be the same as R2 to R1. Again, when I move from R4 to R1, there is no work done because the object is moving or the charge is moving perpendicular to the electric field. Okay. So, this is a plausible explanation for this one. You can show mathematically that this statement actually holds for electrostatic configurations. Okay. So, electrostatic fields have this property that the potential difference is independent of the path and the potential difference depends only on the initial and final points. Okay. Now, here is a very important observation that we can immediately make. Okay. This is so important that I am going to put 2 stars to this observation. Okay. Previous was a 1-star observation, now we make a 2-star observation. What is that? The observation is that you go from R2 to R3, you did no work, R3 to R4, you did some work, okay, against the field. Please note, against the field. Now, you go from R4 to R1, you did no work, but what happens if you move from R1 to R2? This is like you take an object or a man and then carry this object or a man up the hill, okay, and then let the man go. When you have done work from carrying the man from sea level to the mountain top, you have done work against the earth's gravitational field. So, earth's gravitational field is actually trying to pull the man, but you have taken the man all the way up to the mountain top. Okay. So, you have expended that work and that work is the work that we have performed on the charge when we moved from R3 to R4. Okay. You could move on a horizontal scale, but then the potential energy would not change. So, if on the mountain top, if you can move horizontally, the potential with respect to the sea level would not change. However, now if you imagine that you take the person to the edge of the mountain and then just drop that particular person, what would happen? All of the potential energy that we have given to the person so that the person can rise from sea level to the mountain top will now be converted or will now be given back in the form of kinetic energy. The man gets accelerated and then loses all the potential energy, gets converted to kinetic energy, right. So, if I now ask in the same vein, if I move from R3 to R4, I did some work against the field. So, there is some amount of potential energy sitting in the charge now. Okay. Now, when the charge moves from R1 to R2, that movement is aided by the field and not against the field. So, if you assign a sign of minus for the work done from R3 to R4, sorry, plus for the work done against the field from R3 to R4 movement, you should get the same amount of work, you should recover that potential energy when you move from R1 to R2. Okay. So, the work along R3 to R4 will be exactly equal to the negative of the work from R1 to R2. So, once we have done this complete closed path movement, we are back to the same point, right. So, we started from R2, we went all the way around the town and we came back to the point R2. Okay. So, in this particular case, when we came back, we observed that the total work done must be equal to 0. What would it imply in terms of the potential? Well, it would simply imply that the potential with respect to that same point, the difference will be equal to 0. But crucially, there is a right hand side sitting in the expression for potential difference, and that line integral will go to 0 now. So, what we are showing is that if you take a closed path, okay, of the line integral, so you have E dot dl along a closed path, this is equal to 0. Okay. This is very important, and any field which would satisfy this criteria is called a conservative field or a lamellar field. Okay. A conservative is something that I would use because lamellar and everything would be too fluid mechanics for me to use. Okay. So, we have conservative fields which have this property that the closed path line integral would always be equal to 0. Okay. So, what is the takeaway from all this? We can define potential through the work done per test charge in moving along. Okay. You can choose any path to move, but the work done per charge, which is the potential or the potential difference, which so to speak, will be independent of the chosen path, but it will be dependent only on the end initial and the end point or the final points of the path. Okay. And the third and very important observation is that if you move in a closed path, you start from a point, you move around and you come back to the same point, the potential difference will be 0, but in terms of the line integral, that closed line integral will actually be equal to 0. Any such field that would satisfy this criteria is called a conservative field. Okay. With this, now let us go to the point charges that we left off slightly earlier. Okay. I have a point charge. Okay. So, there is a point charge q here, and the electric field for the point charge, we have not actually calculated the electric field. We have calculated electric field for a line charge, but we did not calculate the electric field for a point charge. But we know how to calculate the electric field for a point charge, because if I place any test charge over here, this is my test charge and this is the charge that is whose field I am calculating, then the force on the test charge will be equal to q, and let us call this as small q, q by 4 pi epsilon 0, the charge is kept in air or free space, r square, which is the length or the separation between the source charge and the test charge. Okay. And it will be in the direction that joins the two lines, joins the two charges, the charge q and the charge small q. Okay. So, this is where the charge q is located. Okay. So, this is the force is actually directed along the line that joins the two charges. Now, this is from Coulomb's law. From Coulomb's law, you just simply find out what is the force per test charge by dividing it by q on both sides and remembering all the things that we talked about, how q should be small, q should be large, you can find all those things. You will find that the electric field at any point in space is given by, because of the point charge, is given by q by 4 pi epsilon 0. Let us go back to the vector notation of r minus r and r vectors, and then have r minus r prime. Okay. What is the direction r that we have looked here, or this direction r? Is this the same as the cylindrical direction r? Actually no. For charges which are spherical or which are in the form of a sphere, we have a different coordinate system called a spherical coordinate system, which allows us to work with spherical charge distributions much more easily than other coordinate systems such as Cartesian and cylindrical. So, this r that we have written here in the point charge electric field is actually along the direction of the radius in the spherical coordinate system. Now, it might be confusing because we are using the same letters again and again for different coordinate systems, but that is kind of the nature for this particular course. So, do not be too alarmed, spend a little bit of time in understanding what these different notations are and you will start following them very easily.